Rachael Hughes, and as you can see, she's going to be talking about flexible Monte Carlo realistic bias analysis and measured confounding. So over to you, Rachel.
Okay, so thank you to the organisers for the invitation. I hope you can hear me at the back. Can you hear me at the back? Yeah, I can see some nods, that's good. So I'd first like to acknowledge my co-authors, so Emily Kawabata, Chinyan Shapland, Tom Palmer, David Carslake, and Kate Tillin. All but one of the co-authors is actually here at the workshop. So yeah, if I get a grilling afterwards, I'll pull them down to face you on with me. Okay, I'd especially like to mention Emily. So the analyses I'm going to present were jointly done with Emily. Okay. So the situation I'm going to be talking about is where we want to estimate the effect of exposure X on outcome Y. We've got some measured confounders C of the exposure outcome relationship and some unmeasured confounders U of the exposure outcome relationship. And I'm mainly thinking of an observational study setting and where I would be estimating the exposure effect beta using a regression model. So a naive analysis would adjust for the measured confounders only and assume no unmeasured confounding. Of course, we all know that failure to account for unmeasured confounding or poorly measured confounders may lead to invalid inference. There are several approaches to address unmeasured confounding, both at the design stage and at the analysis stage. And the one I'm going to focus on today is quantitative bias analysis. Oh, hang on, I'm going the wrong way. I always do this when I'm nervous, right? Okay. So quantitative bias analysis is a type of sensitivity analysis, and we can use it to measure the impact of unmeasured confounding on our exposure effect estimate. We can also use it to look at how much unmeasured confounding is required to change our conclusions compared to our naive analysis. Now, a quantitative bias analysis usually requires a model to model the relationship between the unmeasured confounders and the study data. And I'm going to call this the bias model. And the bias model will have one or more parameters which will conceptualize our assumptions about the unmeasured confounding, the relationship between the unmeasured confoundings and the study data. And typically, this is a parameter, let's say, to specify the strength of the relationship between the unmeasured confounders and the exposure given the measured confounders, and another one for specifying the relationship between the unmeasured confounders and the outcome given the exposure and the measured confounders. Now, because we haven't measured U, we can't actually estimate it based on these bias parameters. I'm going to call these parameters that specify the relationships between the unmeasured confounders and the exposure and the outcome bias parameters. Now, we can't estimate these based on our study data. What we can do is once we specify values for the bias parameters, then we can fit our bias model to our study data and then get out an exposure effect estimate adjusted for the measured confounders and the unmeasured confounders given our assumptions specified by the bias parameters. And I'm going to call this the biased adjusted exposure effect estimate. Because we can't estimate the bias parameters based on our study data, we need to bring in some extra information. So this could be information from outside of our study, such as from the published literature. It may be expert opinion. You may have access to data that have measured these unmeasured confounders in another study. Some in the literature, they use the measured confounders that you have to sort of indicate likely values for the bias parameters, and this is a technique known as benchmarking or calibration. Now, there are two broad classes of quantitative bias analysis: deterministic bias analysis and probabilistic bias analysis. In this talk, I'm going to focus on probabilistic bias analysis. So a probabilistic bias analysis requires a prior distribution for your bias parameters. And it's within this we can incorporate our assumptions about the bias parameters. We can specify our plausible values for the bias parameters, value combinations that are most likely to occur, and importantly, our uncertainty about the values of the bias parameters. Using this prior distribution and our steady data, we can then generate a distribution of the biased adjusted estimates of our exposure effect beta. And we can summarize this distribution as a point estimate and an interval estimate. We can conduct a probabilistic bias analysis using a fully Bayesian approach. Roughly speaking, this is where you combine the prior distribution with the likelihood for the steady data. Another approach is called Monte Carlo quantitative bias analysis, and this is where we sample directly from the prior for the bias parameters. We then use those sampled values to fix the bias parameter values to then be able to fix the bias model to our steady data, and we'll get out an estimate of the exposure effect. We'll then repeat this many times to get out an empirical distribution of biased adjusted exposure effect estimates. And the rationale with the Monte Carlo approach is that because the steady data doesn't tell us anything about the unmeasured confounders, there's no benefit to combining the prior distribution for the bias parameters with the likelihood for the steady data. And because of that simplification, you don't need to use sort of a Monte Carlo software or algorithms to be able to fit the bias model to the steady data when you just use the simple Monte Carlo approach. I will describe that in a little bit more detail later on. Okay, so Emily and I conducted a review of software implementations of quantitative bias analysis to unmeasured confounding, and it was the software was extracted from papers published between 2011 and 2021. And we found that programs tended to be specific to one type of analysis. So, for example, just having a binary outcome and a binary exposure variables. And between these software implementations, there was quite a wide variation in the types of methods implemented. And importantly, it's the inputs that the user had to put in, sort of the interpretation of the bias parameters. And also the output that you got out, it varied between the software implementations. And we felt this placed an extra burden on the users having to, every time they've got a new analysis, perhaps having to get to grips with a new quantitative bias analysis method. And we even found this for software implementations applicable to the same analysis of interest. Let's say we looked at a linear regression analysis, and we looked at 5 software implementations. And as I say, the methods varied very much in what they required from the user. And within our review window, we didn't find any programs implementing a probabilistic bias analysis. Now, there are software programs implementing a probabilistic bias analysis. They were just published outside of our review window. Some of you may be familiar with the stated command EpiSens from 2008. There's the R version, which is EpiSens R, and a shiny application, AppySens R. And these are applicable when you have a binary exposure and a binary outcome. You've got 2x2 data, and assume you have no measured confounders. We then have our packages Simtix and Samtix, which is applicable for a binary outcome and a categorical exposure. And then we have our package Conf, which was a paper published on it in 2024. And this really is very flexible. So it implements a Bayesian quantitative bias analysis, and it's applicable when the analysis is a generalized linear model. It allows for 2 unmeasured confounders, which could be binary or continuous. And it doesn't assume independence between the unmeasured confounders and the measured confounders. I have to say, in the review that Emily and I conducted of the software implementations up to 2011, we found that all of the programs there assumed that your unmeasured confounder was independent of your measured confounders in your steady, which isn't very likely. And they were asking the user to think of your unmeasured U as the part of you that's sort of not related to the measured confounders. and think of the bias parameters in that context, which is very challenging. So it was nice to see that the authors of Uncomp sort of made their model a bit more flexible. The only downside I could see to this method was that it has a lot of bias parameters. So, for example, if you have an analysis with a binary or continuous exposure, and let's say you have 10 measured confounders and one unmeasured confounder, then you have between 13 to 14 bias parameters. And if you have two unmeasured confounders, then you have between 27 to 29 bias parameters. And importantly here, the number of bias parameters is linked to the number of measured confounders you have in your study, which in an observational study, you can have quite a few measured confounders. So you're going to have, it's likely you're going to have a lot of bias parameters, and trying to source information on those bias parameters is going to be very challenging. Now, I have to say, in the examples given by the authors of Uncomp, they used validation data. And I think that's what they were thinking, that their command would be used in combination with validation data. And so if you're lucky enough to have validation data where they've measured the unmeasured confounders and the same variables as you in your study, then that would make this a lot easier to apply. So this motivated us to create our own version of a flexible probabilistic quantitative bias analysis tool. And we wanted to make it applicable when you've only got summary data available on the bias parameters. So again, we do it when the analysis of interest is a generalized linear model, and also when it's a survival proportional hazards regression model. We allow for multiple continuous or binary unmeasured confounders, and we don't assume independence between any of the confounders. We require a smaller number of bias parameters, and importantly, the number of bias parameters in our model does not depend on the number of measured confounders you have. So for analysis with a binary or continuous exposure and 10 measured confounders and one unmeasured confounder, we have 3 bias parameters. And if you have 2 unmeasured confounders, then it's 6 bias parameters. So I'm going to describe the bias model in the context of an example. So this is data from the National Health and Nutritional Examination Survey, which is based in the United States. We based our example, on a study published by Butler et al. In 2018. The outcome is waist circumference, and the exposure is a categorical variable with 5 levels. It represents average alcohol consumption in one drinking day. So one drinking day is a day when you decide to consume alcohol. It's not per day. And the reference category is 1 to 2 drinks. And the other categories then are you never drink alcohol, you used to drink alcohol, you take 3 to 4 drinks in one drinking day, or you drink 5 or more drinks in a drinking day. We've got various measured confounders, which are age, ethnicity, education, income, survey year, smoking status, day of dietary recall, physical activity level, and dietary misreporting status. We've got 2 unmeasured confounders. U1 is continuous, and it represents daily non-alcoholic energy intake. And U2 is binary, and it represents marital status. Now, these were actually measured by the NAMES study, and they were included in their analysis by Butler et al. We just, for the purposes of this example, we're treating them as unmeasured. And you'll see later on is because we can actually then look at what would happen if we analysed using the full data. Okay, so our analysis of interest is a linear regression model, and ideally we want to estimate the exposure effect adjusted for the measured confounders and the unmeasured confounders U1 and U2. Note that we're only interested in the exposure effect beta x. We're not interested in the intercept or any of the other coefficients. So of course, this is what we want to fit, but we haven't got U1 and U2. So the rationale behind our bias model is that we simulate values for U1 and U2, where we simulate each unmeasured confounder from a conditional distribution given the exposure and the measured confounders. So for the continuous variable, it's using a linear regression model, and for the binary variable, it's using a logistic regression model. We then fit the analysis of interest using constrained regression, where we replace the unmeasured confounders with their simulated versions, and we constrain the coefficients of those simulated versions to beta U1 and beta U2, which represent what we think is the relationship between the outcome and the unmeasured confounders given the exposure and the measured confounders. And we have to do fit constrained regression here because when we simulated U1 and U2, we didn't simulate it in relation to its based conditional on the outcome. So we have to use constrained regression at the bottom. Okay, but when we simulate U1 and U2, we don't want to have to specify the relationship between the unmeasured confounders and the measured confounders. We want to avoid having to specify those bias parameters. So our way around that is to not simulate the whole part of U1. We simulate the part of U1 that's uncorrelated with the measured confounders. So the bits of U1 that's not explained by the measured confounders. And similarly, we simulate the part of U2 that's not explained by the measured confounders. And I'm going to call U tilde1 and U tilde 2 proxies for our unmeasured confounders U1 and U2. When we simulate the proxy variable for U1, it's again conditional on the exposure and the measured confounders, and we simulate it using information alpha 1x, which is the coefficient telling us the relationship between the original unmeasured confounder U1 and the exposure conditional on the measured confounders. So we're using the information from the previous model to simulate these proxy variables. Similarly for U2. And then when we fit the analysis of interest, we replace our unmeasured confounders with these proxy variables, and again do constrained regression where we constrain the coefficients of these proxy variables to the relationship between the outcome and the original unmeasured confounder given the exposure and the measured confounders. Okay, so this is just highlighting that when we simulate the data for U1 and U2, we're simulating using bias parameters that express the relationship between the original confounder and the exposure and the outcome. And when we do this, we get out our original exposure effect estimate, which is what we want. Not all of the parameters are the same when we use the proxies instead of the original unmeasured confounders. So when we simulate U2, we've got a different intercept term. And for the analysis of interest, the intercept term differs, and so do the coefficients of the measured confounders. But hopefully, well, this is done under the assumption that the user is not interested in the intercept or the coefficients of the measured confounders. So when we're simulating U2, as say the proxy for U2, we simulate it using the relationship between the original U2 and the exposure. But we've also we need an intercept term, which is difficult for the analyst to think about what that is. I mean, they don't tend to be reported in papers. So what we ask instead is for the analyst to give us the prevalence of the marginal prevalence of the unmeasured confounder U2, and then using that marginal prevalence value and the relationship between the exposure and the unmeasured confounder U2, then we can derive this intercept term using a numerical approximation method. And so our bias parameters are going to be the coefficients of the proxy variables U1 and U2 in the analysis of interest, and they're going to be the coefficients of X to simulate U1 and U2, and a prevalence term and a residual variance term. Okay, so we need to specify a prior distribution for our bias parameters, and we do that assuming independent priors for each bias parameter. For the coefficients, we have a normal distribution, and for the standard deviation term and the prevalence term, we use a uniform distribution. So the user needs to enter some information for the hyperparameters, and this is where your external information would come in. So for example, for a coefficient, if you saw a study that had published an estimate for that coefficient, then you could use set the mean as the published estimate, point estimate, and the variance term could be the square of the standard error. In our example, because we wanted to evaluate the model when we had accurate information, we actually cheated because we have U1 and U2. So we actually used our observed data estimates. So for example, for one of the coefficients, we set the mean to be the observed estimate to minus 94.71, and the variance term was the square of the accompanying standard error, which was 19.64 squared. Okay, so I'll now talk through the Monte Carlo approach. So this is just a set of steps that you repeat many times. So you first make a random draw from the prior distribution to get values for your bias parameters. You then fit the bias model to your study data, fixing the bias parameters to the drawn values from step 1. So in there, we then simulate our proxy variable for U1, simulate our proxy variable for U2, and fit our constrained linear regression using these simulated proxy variables that we've just simulated. You then get out of step 2C, you'll get out a point estimate and a variance term for the exposure effect. You use these in step 3 to add some random sampling to the estimate of the exposure effect from 2C. We do that using a normal distribution. And you repeat steps 1 to 3 many times to give you an empirical distribution of the bias-adjusted exposure effect estimates, which you can then summarize. So we summarized it where we set the median as our point estimate and our 2.5th and 97.5th percentiles as the endpoints of our interval estimate. So we compared various methods. So because we have U1 and U2, we could actually fit the analysis of interest to the data. So that's the full data analysis. And then we looked at our naive analysis where we only adjusted for the measured confounders. Then we did our Monte Carlo quantitative bias analysis using our proposed bias model and prior distributions, and we did this with 10,000 repetitions. So we got out an empirical distribution of 10,000 bias-adjusted exposure effect estimates. We then did a fully Bayesian implementation of our proposed bias model and bias parameters, priors for our bias parameters. With one exception, so we figured the same as we did for the Monte Carlo, with one exception. So we used the R package and conf, and we couldn't specify a prior for the prevalence term and then derive the intercept term. So instead, what we did is we directly put a prior on the intercept term used to derive the proxy variable for U2, and we made sure this was equivalent to our prior on the prevalence term. And we also specified vague priors for the parameters that we estimate when we've fit the model to the data. So that's going to be, in the analysis of interest, that's going to be the intercept term, the exposure effect, the coefficients of the measured confounders, and the residual variance term. So the Bayesian analysis was done with 22,000 iterations. We threw away the first 2,000. And we also summarized then the posterior distribution of each exposure effect coefficient with the median and the 2.5th and 97.5th percentiles. So here's a plot showing the results. So on the vertical axis here, we have the results for the 4 coefficients of the exposure effect. So at the top, we've got the coefficient for never drank. Then we've got a former drinker, 3 to 4 drinks, and then at least 5 drinks on the bottom. And then on the horizontal axis, we've got the mean difference in the waist circumference in comparison to the reference group of 1 to 2 drinks per drinking day. So the results in red are those belonging to the full analysis. This is where we were able to adjust for the measured confounders and the measured versions of U1 and U2. And the one in black is the naive analysis where we only adjusted for the measured confounders. And you can see that although there's a lot of overlap, so they're quite wide confidence intervals, there is a bit of shifting here when you only adjust for the measured confounders. The results in pink are the results from our Monte Carlo bias analysis, and it's nice to see that they closely match those of the full data analysis. Obviously, well, this is reassuring because we have accurate priors here. We centered them on the right value, so it was good to see that we got that, and also good to see that our results were very almost identical to those from the fully Bayesian analysis. So we did evaluate our bias model in lots of different scenarios. I'm not going to discuss those, you'll be relieved today. I'm just going to describe 2 scenarios that we looked at. So we looked at the setting scenario A, where the analysis of interest is a logistic regression, and we have a binary exposure and 1 unmeasured confounder that was continuous. And then in scenario B, we have where the analysis of interest is a linear regression. We have a continuous exposure, and we have 2 unmeasured confounders, both continuous. We got some measured confounders. There's just 3 of them here. One's categorical, one's binary, and one's continuous. And the data generating models for these scenarios were based on a real data set, the Barry-Caffili growth study. We simulated 500 data sets, each with 1,000 observations. So the methods we compared were the full analysis, where we fitted the analysis of interest, including our U. Then we did a naive analysis where we just adjusted for the measured confounders. We did a Monte Carlo bias analysis with 100 repetitions. And we did a Bayesian implementation with 4,000 iterations, of which 1,000 were burn-in. For the prior distributions for the bias parameters, so again, we used, similar to what we did for the real data application, we used normal distributions for the coefficients, uniform distributions for the variance terms, and the prevalence, so that's not in this particular scenario, sorry. Note that we wanted to evaluate this model when we had accurate priors, so they are centered on the true value. So we wanted just to check that we got back what we should, the exposure effect estimate. And we looked at 2 settings. We looked at when we have very informative priors. So we defined this to be that 95% of the draws from that prior would give us values that were within 10% of the true value. And then we also looked at a setting where 95% of the draws were within 30% of the true value. Okay, so you might not be able to see this on the back. So we've got 2 plots here. On the left-hand plot, your left hand, we've got the results for the bias of the exposure effect. And then on the right, we've got the coverage. So the results in black correspond to scenario A, where we're fitting a logistic regression. And the results in red correspond to scenario B, where we're fitting a linear regression. And So obviously for the full analysis, we would expect unbiased results or minimally biased and nominal coverage. And then by design with the simulation study, when we do the naive analysis, we get biased results and we get poor coverage. When we did the Monte Carlo bias analysis with both the very informative priors and less informative priors, we actually got back to what we had with the full analysis and close to nominal coverage. And we got very similar results with the fully Bayesian interpretation too, fully Bayesian analysis too. And as I say, we looked at this across lots of different analysis scenarios and we got the same results, which was encouraging. Okay, so just some final remarks. So we proposed a flexible probabilistic quantitative bias analysis approach. And I'm really interested to see whether I can use this same bias model to conduct a deterministic bias analysis. Importantly, our particular approach has a relatively small number of bias parameters where they don't depend on the number of measured confounders you have in your analysis of interest. I'm currently writing this up as a Stata command, QBA confound, which I'm hoping to present at the UK Stata conference in London this September. Actually, I'm on the scientific conference for that. So if you're interested, please submit an abstract. It's the 3rd to the 4th of September. Also very interested in doing an R package version as well. Obviously, with the bias analysis, the really difficult bit is getting the external information. It's a little bit like what Kate Tilling was talking about yesterday in terms of triangulation. This is the part that often is not really addressed at quantitative bias analysis, in papers on quantitative bias analysis, including by someone like myself. I'll just say something in the discussion mentioning how difficult it is. And it is something I'm really interested in looking at, trying to help analysts get this good, reliable external information, because as you can see, the reliability of the sensitivity analysis depends on getting this good information. And further work could be applying this QBA confound in other settings, such as can we do it when you've got a weighted analysis or you've got a multi-level analysis and so on. So I've got some references, and then just to say we do have a paper on medRxiv on this, and it's currently under review. Thank you very much.
Good. Okay, time for questions. Vanessa?
Great. I'm everything relies very much on parametric assumptions, right?
Yes.
Very parametric models, and but against the trend in causal inference where we want to go more semi-parametric or non-parametric. I was wondering, but and you might also worry just as much about unspecified models as about unmeasured confounding. So if in your literature review, did you find any example maybe less parametric, and where this software implementation that could be used? Have you looked yourself into violation of those model assumptions, or what other things that can happen then?
So no to the latter question. I haven't looked at whether there's sort of most of the software implementations did assume some parametric assumptions, and I suppose I come from the imputation world where I'm quite happy to do that. But I do recognise, the assumptions of how much it works does rely on that. And obviously, I simulated data in this perfect world where everything was correctly specified. So yeah, that is a weakness of the method.
With Kate, we have this paper on missing data where we show that the method when the whole model is misspecified, the method that's usually correct for the right model can be quite wrong and even worse. And so it is something that's worth thinking about.
Yes.
I think so.
Yes.
If we find this with missing data or multiple imputation is appropriate. So
absolutely. Yes. Yes. No, I agree. That is criticism of the approach. Yeah.
Thank you for a very true talk. So I just wanted to hear your thoughts on the case for your multiple plot is oftentimes even the annual data we choose other measures or weight or EMI, but then without kind of a quantitative bias analysis. And just curious what your thoughts on how you would incorporate that into your framework that you set up when we have whole plot and we want to do that
Oh, okay, so you're doing like a bivariate analysis or something.
Yeah, let's
Yeah.
say like I'm interested in the primary outcome and secondary outcome.
Oh,
And I
okay.
just have a specific question, maybe, of all of it. In that case, how many unmeasured confounders would you think to consider? And that, I guess it can be a little tricky question, since it said that there'd be one unmeasured confounder that affects only the primary outcome, but not the secondary outcome. But, and I just wanted to, I know you'll be focusing on the scalar outcome case, but just wanted to have your thoughts on how you might incorporate those scenarios.
So I haven't thought about that. Obviously, it just it increases the number of bias parameters you have to think about, and I don't know whether it would be. I thought my first thought is that you would just tailor it to the particular outcome you're considering, which ones would be the unmeasured confounders for that particular outcome, because you'd want to limit the number of bias parameters, because that's the bit that's difficult to specify information for, and it is really crucial. So I think that's my first answer.
Yeah.
So I guess following on a bit from what Vanessa asked, when you showed the results for your simulation study, where you had the informative and then the very informative parameters, it didn't seem like that made much difference to the results, which kind of went against my intuition, I suppose. You feel like the more accurate and precise information you're putting in might affect.
Well,
certainly the coverage, but maybe it's just the.
Yeah, it's possibly if you looked at the numbers in the tables. I mean, they were both accurate, but at different levels of precision. So you would just expect wider confidence intervals.
So you did see.
Yes.
Yeah.
And it's if you we did look at the situation where you have slightly inaccurate, so you're not centered on the true value, and it's beneficial then to have a little bit more uncertainty to get coverage. Yeah.
There's a question there.
Thanks a lot for talk. This is related to earlier points. So it seems to me like your model has quite a few bias parameters, and you need to come up with a good prior distribution for them to make the sensitivity analysis work. So I'm interested in hearing your thoughts on like how hard it is for practitioners to describe these prior distributions, and I need a sensitivity analysis rests on this assumption. And second, if you think this method is kind of hackable in the sense that you allow applied people to specify very narrow distributions, and then people may claim they've done sensitivity analysis when they really kind of just hit the model.
Okay, so I suppose to perhaps get around that hackable bit would be to have guidelines like you do in the missing data literature, that you have to account for your uncertainty and maybe specify things before you do the analysis. So you're, I would say, yes, it would be difficult for users to specify the prior distributions, and some guidance on that is really helpful. In the software we're developing, we're just not allowing the use, we're fixing the prior distributions. It's just the normal distribution for the coefficients and so on. But yes, some guidance would be useful for users, like a nice tutorial paper on how to choose the prior distributions. And yeah, I had help from Qing Yang for this. Don't know if she's in the audience, but thank you, Qing Yang. Oh, hi, Qing Yang.
We have time for more questions, yeah. Go ahead.
Thank you for the talk. I was just wondering, especially in the logistic case that you were showing the simulations, how do you distinguish between the bias that comes from your unmeasured confounders and like your own collapsibility?
Yeah.
That leads to a different estimate if you take into account more covariance in your condition.
Yeah, so I was a bit wary about writing that in the paper. So we didn't distinguish between it. We just said this was the results you get from just adjusting for the measured confounders. But yeah, you're right that with the non-collapsibility, you're conditioning on different sets of, when you're comparing it to the full data analysis. Is that what you're concerned with?
Yeah, so is that taken into account automatically? Like the non-collapsibility problem, is that taken into account?
So really interesting comment, because we just got comments back from the reviewers, and that was one of their queries. So I always thought non-collapsibility is a problem when you're conditioning on a different sets of variables. In the bias model, when we derive the bias model, we're always conditioning on the exposure and the measured confounders. So I don't think it's an issue there.
But is but maybe I don't understand what are you really targeting when you have when you're including the additional confounders that you don't have, because in truth you want to condition for them, I guess. Like for example, in your simulation you said, or one of your examples you said clearly leave out these confounders and you see them as magic confounders. So we think if you had the confounders, you would have adjusted for them.
Yes.
But would then be targeting a different estimate.
So the one that I'm targeting is the one where we actually adjust for the unmeasured confounders and the measured confounders. That's the bit I'm targeting.
Yes, that's I think what you would want. And so my question is, are you then taking the difference in estimate also into account in an approach? If we can talk about.
I think we need to. I don't think I fully understand your question. Sorry.
Maybe time for one more for someone. Yeah, go ahead.
This seems to be an excellent model for known unknowns. What about the unknown unknowns?
Yes, that's where I think perhaps a deterministic approach would be better, where you perhaps have a plot showing, like for different values of the bias parameters, and you could look at the plot to see whether, you know, within a range that I think is plausible for this unknown unmeasured confounder, which ones does it change my conclusions? And what you hope is that your conclusions don't change within that range, and then you can be reassured. So yeah, I think this approach is really for when you've identified what the unmeasured confounders are. Yeah.